All right, so in the last class, we continued our discussion on latches and flip-flops. Remember, we looked at a gated SR latch, gated D latch. We looked at the flip-flop variants of the latches, where you have two latches connected back to back. We looked at the timing diagram, and we noticed that it is possible to get rid of the 1-1 overlap problem in a SR flip-flop by using a new design approach, and that is a JK flip-flop. And we noticed that JK flip-flop had an interesting feature where both J and K become 1, the output toggles. So the output just changes. And then somebody came up with an idea to use this feature specifically to design a different kind of flip-flop whose only purpose will be to toggle the output. All right. So this is the T flip-flop whose only purpose is to toggle the output. All right. And then this is where we are right now. This is the end part of the sequential logic lecture. So I'm very happy because this is a very important concept, kind of also unique concept for digital logic design. And for the most part, many students often remain confused or less informed in the flip. I was told by my senior colleagues who had experiences dealing with students who go up the chain, like from 255 to 300 to 400 level, that people didn't really study flip-flops and latches. So I tried to make it meaningful, but I mean, that's why I want to take a quiz on this topic specifically, just sequential logic. I will declare that I will post an announcement about it. So next quiz will be specifically on these two lectures, just on flip-flops and latches. That's all. Because this is very important. I want to make sure that you understand this properly. All right, so we are taking the last right. And very important concept about sequential logic, because sequential logic deals with sequence and timing and waveforms, right? So we have to be mindful of the timing metrics. What kind of metrics define the performance, and what kind of metrics have to be met to a certain level to make it work? So we will talk about all of them today, and we'll learn a lot of new terminologies that are kind of like everyday jargons for engineers in the industry. All right, so let's get started. What you see here is a simplified timing diagram for a flip-flop, right? Super simple flip-flop. So I'm just taking it as a D flip-flop without any loss of generality. Give me 1 second. It's not letting me erase, so I'm just going to restart again. All right, so this is your clock signal, and this is your data, and this is your output for the flip-flop. Super simple. A D flip-flop sends the data to the output at the positive or negative edge of the clock. I hope by now we are all on the same page, right? Okay, without any loss of generality, I'm gonna take the positive edge every time moving forward. But if you have a question, why positive edge? No reason. I could just take the negative edge as well. But you have to take one of the edges, either positive or negative. All right. So this is a D flip-flop. This is your positive edge of the clock. So at that edge, the flip-flop takes a look at the data. It says, oh, the data is 1 now. Let me send 1 to the output. And we are assuming, just to show you the change, that the output was previously 0, right? If you draw the history, then maybe you see that the output was 0. That's what we are assuming. Okay, so now, see, every day there is a new technical challenge. Now, this erase option is disabled for some reason. I don't know. That's a bad apple. Anyways, so, okay, the point is, this is your data, and it changed from 0 to 1. Notice it is changing before the clock edge appeared, and that is deliberate. We are getting there. For the time being, just take it for granted. So your data is 1. When your clock edge appears, you just look at the data and you send it to the output. But as I told you before as well, but we didn't stress on this, that, hey, you don't see the change right away at the output. The output cannot instantaneously copy the input. There is a time delay, because everything, as I told you, is essentially about charging up capacitors and discharging capacitors. Whenever I say that a voltage will go from 0 to 1, the way it goes from low to high would be by charging up capacitors. Remember, capacitors, inductors, and resistors make up every possible complex electronics that you know. Okay, even superconductors, for example, that have no resistance, they still have inductance, for example. All right, so these three components will be forever with you in electrical engineering, no matter what kind of fancy technology you're dealing with. Now, keeping that in mind, when I say that your output will go from 0 to 1, there is a charging process involved, which takes time, and that's why there will be a delay. And this delay is called clock to Q delay. And get used to this term because this is the standard terminology you always use. Why clock to Q delay? Because we measured the delay from the clock edge. Remember, clock is the boss. Whenever you get an edge, action starts. So you start counting, you start your stopwatch when the edge appears, clock edge appears, and then you stop when the output actually stabilizes, right? So you look at the edge of the clock up to whenever the output changes. This is your clock to Q delay, and oftentimes it is written this way. I hope you can see that clock to Q delay. In some textbooks, in some literature, they prefer using it as propagation delay, TP, propagation delay for flip-flop, FF. Sometimes they write it this way. If you see data sheets, if you see some documentations from some industry, you'll find it either in this format or the other format. Very standard. Are you all good so far? Super simple. I'm going slow deliberately because I want you to get it, not just, oh, okay, clock to Q delay. Because some towards the end of the lecture, there will be 2 slides that will be a little bit more involved. So I'm building up to those 2 slides actually by going slow. Okay, next. The next concept is called setup time. Okay, here is what it means. So you have your clock again, which is the easiest thing to explain because there is nothing to explain. It's something that you control. And then here is your data. Notice you want to change something in your data input. You want to go from 0 to 1 or 1 to 0, doesn't matter. You want to change something. Whatever you want to change should appear well in advance from the clock edge. Okay, that is the rule. And I'll tell you the reason in a second. But the rule is if you want to change your data, it has to be done a certain amount of time before the clock edge appears. Okay, so you have to do well in advance. For example, if you want to terminate your apartment lease, you have to inform them 2 months ago, for example, 2 months ahead of time. That is essentially the setup time for lease termination. Okay, similarly, whatever changes you want to make to the data must appear before a certain time, and that time is called the setup time. And it is also measured, surprise, surprise, from the clock edge. And I told you, clock edge is the boss, right? So you look at the clock edge and you see, you assign a certain amount of time that creates a gray zone. Within this time window, you cannot change the input. Even if you do, what happens when you do, right? Whatever change you make will not be reflected in the output. So the output will be garbage, essentially. Does that make sense, folks? Okay, so you need to change your input well in advance. This time is called setup time. So, and it is mentioned here, data D must arrive. There are different ways of mentioning that. You must stabilize the data, or the data must arrive. Why are we mentioning about arriving? Because typically you are dealing with a chain. Okay, the data is coming from a different portion of the circuit. So remember ripple carry adder, where the carry was rippling through multiple stages. So at one of the stages where you have the flip-flop, you want to make sure that the data has already arrived before your setup time. If it arrives during your setup time, that will be treated like mistreated essentially. All right. Okay, simple concept. So we know about setup time, we know about clock to Q. Let me show you a quick example of a setup time violation. Okay, so this is your clock signal, and the red dot marks the setup point. So you need to have your data ready by this time. So this is your setup time. Can anybody notice the second row and tell me what's wrong here? What's wrong? This is your setup time window, right? Within this time, flip-flop needs its own rest. It doesn't want to take any kind of input changes. However, your input changed in between the setup time. So this, yeah, we are showing that this change was reflected, but this will not be reflected essentially. It may not be reflected. We don't know. It may or may not be. So Remember, we hate unpredictability because digital logic has to be predictable. Every bit of information is crucial. And I hope did I give you this example of cat and bat? Remember in the very first class, a single bit flip could lead to disaster. More critical than cat and bat, by the way. Imagine your bank statement or bank numbers, the amount of money you have in your, if one digit changes from 1 to 0, it could eliminate, like just imagine 1 million to few K if it is the most significant bit, right? Anyways, my point is every single bit matters. So if you do not know whether your output will be valid or not, you cannot trust your output. That's when everything has to be cleared. So if something like this appears and the system, there are always checks and balances that we have in place. If for some reason we detect that there has been a corruption of the data, we erase everything and we restart typically, right? We reset the system. So you don't want to do that every time. So this is an example of setup time violation. In this example, you see that the queue still changed, but it may not change. We don't know. We just don't know. That's why we don't want to get to this situation. Okay. Now, third, setup time, clock to queue. Third concept is hold time. So similar to the setup time, for example, the flip-flop needs a certain amount of time of rest before the clock edge appears. It also needs stability after a certain amount of time from the clock edge. Okay, so after the clock edge appears, it does not want to take any input changes. So whatever changes appeared must appear before the setup time. So this is your setup time. It should appear before the setup time. And once the clock edge appears, the input must be stable. It shouldn't change for at least a certain amount of time. That is called the hold time. Okay. Are you all with me? Okay. So this is your hold time. Let me see if I can. I cannot erase, so I'll have to restart this slide again. All right. So this is your hold time. Notice your data was stable for the entirety of the whole time. It changed afterwards, but you don't care. Okay. Are you all good? Yes. Yes, that's a great question. I was going to talk about it, but thank you for indicating that I haven't talked about it yet, right? So that makes it important to talk about. Okay, so what is the origin of setup and hold time? And I already mentioned this indirectly. That is capacitors, essentially. So remember, every circuit at some point when you take 433, honestly, I keep mentioning that because only then you start looking at the nitty-gritty details of the circuits, and you see where there is a separate lecture on parasitics, essentially. Parasitics stands for capacitors, inductors, something that is more like a residual component of the circuit. You don't connect capacitors, okay, in a digital logic. You don't connect capacitors. They come for free with the MOSFETs, with the transistors you use, okay? And then when you drive inputs, you are essentially charging up capacitors. When you drive output, you are also driving up capacitors or driving down, like charging up or charging down capacitors. So once you start charging capacitors, imagine you want to go from 0 to 1. Just, don't look at the slide. All right, let's discuss this just, verbally. Imagine when you decide that my input wants to go from 0 to VDD, and you start charging the inputs. So you need to let it finish charging, right? Otherwise, imagine while it is charging towards VDD, you suddenly decides, no, my input will go to 0, right? You suddenly go to 0. And while it is charging, it starts discharging again. So it's not going to complete anything. It will not go to VDD. It will not go back to 0. It will be stuck somewhere in the middle. Does that make sense? So that's what leads to disaster, because digital electronics doesn't recognize anything between 0 and 1. There has to be either 0, and VDD essentially means 1. Okay? It has to be 0 and 1. So you have to let it finish charging. Even if you want to go back to 0, that's fine. But first let it finish charging, go to VDD so that you don't get stuck at an intermediate stage. Okay, let it finish charging. And then you go down to 0, it will discharge again. It doesn't mind. The capacitors don't mind. They will charge and discharge the way you say it. But you have to let them finish what they started. So setup time is about, say, they started charging or discharging. You have to let them finish. So during that time, you have to keep the data stable. That's the setup time. You're letting it set up. And after it reaches a level, You cannot just abruptly change the data because everything takes some time to, go down or go up again. So essentially, it all comes down to this very simple phenomena of charging down, charging up, or charging down capacitors, discharging capacitor. Are you all good so far? Okay. But imagine when you're dealing with millions of components, can you keep track of every capacitor's charging up, charging down? Can you do that? Is it even possible? No, you cannot even count the capacitors because they're part of their parasitics, essentially, like I said. So you cannot really always count how many capacitors. It is not a valid question. You cannot count the capacitors because you're not connecting any capacitors at all. They're part of the structure, okay? So the way you make it digestible for circuit designers would be by taking it as a macroscopic parameter, like setup time. You see that by experiment, of course. It doesn't happen overnight. You experiment with flip-flop. Remember, I told you there is a guy in industry, say Intel or AMD. You are the flip-flop guy. You design a flip-flop circuit, you test it, you improve it, and you keep working on flip-flops throughout your life. So you're the flip-flop person. If something goes wrong with flip-flop, they will catch you. Does that make sense? There is an XOR guy who is focusing on making the best possible XOR circuit. Two input XOR, three input XOR, blah, blah, blah. Right? So what do you think they do? They will characterize everything for you. They will characterize how long it takes to stabilize the input, how long it takes to stabilize the output, all these metrics. And they will give you a number. Hey, make sure that your data doesn't change 5 nanoseconds before the clock appears. And it doesn't change 10 nanoseconds after the clock appears. They will give you some numbers. Make sense? So you can get it through simulation, but they also do experiment because in case you missed something in the simulation, experiments will catch it. So eventually they pack it into macroscopic parameter numbers like setup time and hold time. So these are essentially macroscopic parameters, but they are linked to fundamental charging, discharging of capacitors. That's all. Are you all good? Okay, these are meaningful. They are not like random numbers that we just said, hey, this is the rule. You have to set it up 5 nanoseconds before. You have to set it up because every technology generation, once you change the transistor, these numbers will have to be recalibrated. You have to measure them again and tell me how long. And obviously, they keep a margin. You don't want to operate at the edge. If they see that it needs 2 nanoseconds, they will ask you to keep 4 nanoseconds, for example. So I hope that makes sense. All right. So notice, after the clock edge appears, your data remains stable for a certain amount of time. That is the hold time. Okay. Now, let me show you a violation of the hold time. Notice, I hope you can detect this easily. And we are taking simple examples here to let you settle down. So this is your hold time window. Within this time, you don't want any changes to the input either. What happened here? Is there any problem that you see? Do you see any problem here, folks? During the hold time window, your data started changing. You don't want that. During setup time and hold time, your data has to be stable. But okay, so let me just draw it from the scratch in this section. Okay, imagine you have a clock edge. This is your clock edge. There is a time window before and there is a time window after within which the data shouldn't change. That's the time before the clock edge is called setup time. The time after the clock edge is called hold time. You have to set it up well in advance and you have to hold it for a while. That's the rule. All right. Now, after all this, nitty-gritty understanding, we are ready to see there are two fundamental constraints that govern the sequential logic design. It is so critical that there is a specific design step, no matter which industry you work for. There is a specific design step associated with making sure these two constraints are met. So you use a simulator, you test them until you get rid of all sorts of setup time violation and hold time violation. And I'll show you. Let's start with setup time constraint. This is the number one constraint. And the second constraint will be hold time constraint. What do I mean by the constraint? Basically, it's a design rule that you have to follow. Okay. Now, this is a flip-flop A and flip-flop B. And in between, there is combinational logic. Do you guys remember that I talked about this structure before? In which context? I told you how combinational logics and sequential logic are intertwined. Why do you need sequential logic? Because you want to synchronize everything. You want to control everything in a measurable, trackable way. You, combinational logic will keep changing the moment the input changes, right? But sequential logic will not. They will hold on to the output until and unless you give it a certain environment to flip or change. You have control over the sequence. So what we do is we have blocks of combinational logic. What kind of combinational logic circuits have you worked with so far? Mux, multiplexer, ADC, and like DAC, multi mux, demux, adders, right? There are many others, of course. So whatever, these are all combinational logic. And then you have this combinational logic block here. And before and after, you will always have flip-flops that will help you synchronize. This flip-flop will start providing inputs to the combinational block, and the next flip-flop will help you take output from the combinational block. Okay, so now in between these two, notice you have a clock that is feeding both blocks, flip-flop A and flip-flop B. The same clock signal is feeding both of them. Okay, and it's, I mean, if you're surprised looking at one signal driving two, remember a clock signal can drive thousands of flip-flop. Like there is one mother clock signal that drives everything. Okay, so clock routing is a very big step for VLSI design. Okay, all right. Oh, not getting ahead of myself. Let's see. So you have the same clock that is driving the flip-flop, first flip-flop, flip-flop A, and the second one, flip-flop B. Okay, now let's talk about the events that appear in between these two flip-flop. First, when the clock edge appears, your flip-flops will only respond here at the positive edge and here at the other positive edge. In between these two edges, they will not do anything. Okay, so when this edge appears, there will be a delay. Imagine you have something, data at the node P. So this input will go to output Q, right? To go from P to Q, you have a delay. What is the delay called? Clock to Q delay. Or I told you that it could also be represented as the propagation delay, TP for flip-flop A. So I hope you can now understand the meaning of these terms. TP stands for propagation delay, FF for a flip-flop, and flip-flop A. Okay. So now your data has come to Q, but it still has to go through the combinational logic block. And combinational logic has delay. I told you, remember we talked about multi-stage logic. The more stages you have, more delay will there be, right? So obviously combinational logic block has its own delay. It is not called a clock to Q delay. Why? There is no clock in combinational logic. It's not a clock to Q delay. It is simply propagation delay. So it is called TP, propagation delay, for combinational block. Are you good? Okay, so after a delay, this Q goes to R. And then finally, flip-flop B gets the input. But this is your setup time for flip-flop B. Notice, this is a setup time for flip-flop B. Flip-flop B will only receive the input, which is, coming all the way from flip-flop A's input. Flip-flop B will only receive it given that it appears when, folks? Given that it appears before the setup time. Does that make sense? So when the clock edge appears, that's when this flip-flop B starts responding, right? But your input, which is coming all the way from the very first input, P to Q, Q to R, it should finally appear at the D node before your setup time. Do you guys all agree? So this clock edge, notice we have deliberately drawn it in a way that the clock edge appears at the perfect time. Like right after the setup time, the clock edge appears and the flip-flop starts responding. Are you all good? Now, I will draw two cases. You have to notice and respond. All right. Number one, case one. And I mean, ideally, I would have just erased it or use a different color, but now I have to deal with the technological issues. So imagine case A, please notice as I draw. Second clock edge appears here. What is the challenge? What is the problem? Can anybody tell me what the problem is? Yes. Yeah, so first of all, we haven't even looked at this whole time yet. You know why? Because whole time occurs after the clock edge appears. After the clock edge appears, you start responding, you want your data to be stable. Okay, that's where hold, the concept of hold comes. So we haven't started looking at the whole time yet. We are looking at, and by the way, notice, we are looking at the flip-flop B's perspective. Flip-flop B wants the input to come. And flip-flop B wants that input before its setup time. Okay? But the input is coming through the flip-flop A and then through combinational logic. So there are two delays associated with it. Even when you provide the input to P, it takes a while to get to this level, R. Okay. The problem would be, this is your setup time. This is how much time the flip-flop B will need to stabilize. But if your clock appears before this time, that means, will you get enough setup time, folks? No. So that means flip-flop B will have a setup time violation. So you cannot trust the output eventually. Does that make sense? Okay, I will, don't worry, we will repeat it as many times as needed, but let me just also show you the other perspective. Case B, please notice, and you'll have to tell me the problem with that approach. And maybe, I mean, in another day, I would have given you some extra credits for it, but I'm not prepared to take notes here. But feel like you have some extra credits for it. So I'm going to say that if your clock edge appears here, what will be the problem? Or will there be any problem? First question, will there be any problem? Do you see any problem here? The clock edge appearing later, slightly delayed. Yes. Okay, so thank you. Yes. By the way, that's a good perspective. Let me clarify. Hold time starts after the clock edge has appeared. So if your clock edge hasn't appeared, there is no concept of hold time at all. Once the clock edge, why we do have this concept of hold time? Once the clock appears, I start responding. And once I start responding, I want you to let me finish. It's kind of like that. You know what I mean? So the flip-flop, once it starts responding, it wants to get some time to settle down. It doesn't like an input change while it is responding. Does that make sense? So we haven't seen any hold time related concept here because the clock edge hasn't appeared yet. So we stop in this slide, wherever the clock edge appears, we stop there. Okay. So as of now, I'm hearing that we don't have any concern with it. The clock can appear later. It has enough setup time. Do you guys all agree with it or disagree? Anybody wants to? The worst thing you can do is not try. And because here we have a friendly environment, you have the right to make mistakes. In your actual job, it will be embarrassing to make a mistake and it could be detrimental in general to make mistakes. Okay. World is unforgiving in general. Survival of the fittest. You know, Amazon laid off like 16,000 engineers a couple of days ago, right? And they said that they will lay off 30,000. So, I mean, this is not new to us anymore. We know this ever since I was in college. I know every once in a while, big companies lay off people. You know why? They try to make it a competition. If you become complacent, like, hey, you are a good engineer, we hired you, we are paying you enough, you're great, you have really nice life, you're going along, you're going places, visiting Europe, right? Going on cruise, whatever. So you are, but that means you're not being pushed to your limits. But they want to push their employees to the limits so that they can extract the whatever you have in it, whatever performance you have in you, they want to extract everything. It's like, you know, cold pressing olive oil or something. right? Like literally getting everything out of you. But they cannot do that unless they put you guys in a competitive position. So if you're always on your toe that, hey, I might be get laid off next if my performance numbers don't look good. You might be very good, no doubt, but there is someone better. And n- do you know they personally know these 30,000 people? No, I cannot even personally know 300 people actually, right? 30 is also a stretch sometimes if you want to really know them. So 3,000, 30,000, nobody knows them actually. All they do is they see numbers and metrics, performance metrics. Who gives this performance metrics? Your group leader, and group leaders have their leaders. They have their lab leader. There is always a hierarchy, by the way. Everybody is graded, including the CTO, for example, right? Even CEOs get fired, as you know, by the board of directors. So they all have their performance metrics and their uh, so everybody is judged. So now imagine I'm a group leader. I have 10 people under me, and I want to assign some grades. The way I know this because I worked in, I remember I worked in Samsung R&D for R&D, like research and development section for Samsung for about 2 years. And I've been through this process. Your group leader is given just one A, and then A minus B, C, D, blah, blah, blah. If you get C and below, you can be fired immediately, right? So just one A. And everybody is working hard. Everybody is doing good, blah, 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 right? And they're all friends. We are working together in the same team, but only one of them will have an A. So imagine, I will think twice before collaborating with my friend and helping them out with their circuit design. Hey, you're stuck. Let me help you. Right? Okay. Because this guy might get an A and I will be in the lower stack. So eventually, you have like so many employees. If you fire 30,000 people, just imagine how many you have. Right? I have nothing against Amazon. This is a recent example. That's what I'm bringing up this example. All right. So they might decide whoever got A will remain. Even if they choose to do so, there are so many people that will have enough people to remain. So only the best people in every group will remain. Everybody else will be let go. Can you just imagine the stress? I'm not trying to freak you out. This is every industry in general, most of them actually, that try to use this strategy to make always keep you on your toes. So you're always like, there is no extension to homeworks. There is nothing. Okay. And one other thing, I mean, this is a tangent. I know, like but this is important essentially. All right. Uh, I want to create a philosophy rather than just give you grades. And at some point in life, you will see nobody asks me about my grades anymore. Even if I want to, hey, my grades were something, right? But nobody cares anymore. At some point, this will all be forgotten. You needed them now. Don't get me wrong. You need them now to get to the next level. But what you need more is to develop the aptitude and the habit of taking challenge and participating and being vocal. In a team meeting, I'm the group leader. There are 10 engineers under me. Whoever is the most vocal, and not just vocal with random stuff, whoever gives me real input, I like that person. You see my point? So you have this in your head, you know everything. You are much smarter than others, but you don't talk. You don't respond. You don't give opinion. You don't point out my mistakes in a polite, hey, I don't think you're doing it right. This is how you should do it. I will appreciate if you save me from making a mistake, which will get me in trouble later on, right? Rather than, yeah, you're good, boss. You're right, you're right. Like, yes, man, right? If you have a yes man in the group, at some point they get caught. They're like, you say yes to everything, so you're not really useful. And these are reflected in your yearly like review. So every time you get below the stack. So there is a constant competition. Everybody is competing with everybody else. You are friends, but still you might have coffee together. You might, go out and talk. But in the end, you'll be judged against each other. And you don't know. One of them will be let go. So this is a serious challenge in real life. And real life is essentially like this, right? You just don't often have a second chance. Even if you do everything right, you might still be let go because somebody did it better. Both of you did the right thing, you are good, but somebody was slightly better. And the top level management decided we will only keep the people who got an A. The person who got an A minus was equally good. I remember in the team, I'm not giving you specifics. Uh, there were two people who were like really competing with, and we were like very close friends. Thankfully, so our group leader was like really, really at a loss as to who to give an A basically, because it's risky for the other person and it is unfair because both of them were so good. So one of them had one patent more than the other one, just one patent more than the other one. So basically, just imagine. And the people who worked for a year but didn't have patent, equal number of patent, they were like B and B minus and whatever. So anyways, because they push it, even if I in my class, if all of you get an A, I don't mind. I can give you all of I give all of you an A. That's why it is not really reflecting the real life. In real life, imagine in if the department decided I can only give an A to one of my students among 90 of you, just one. Wouldn't that be a really competitive situation, right? I know there was a professor at Purdue who used to do that. Like he decided to get in. There was just one person in the group who will get it. So now I realize the reason. At the time, nobody liked it, but now I see. I mean, that makes sense actually. Even if I get an A minus in that course, that will not honestly change anything in my life further down the. If I really learn to be competitive and responsive. So I want you to succeed in life. That's why I'm pushing you to respond and ask questions and ask intelligent questions. That's what gets you ahead of the pack. Because honestly, you will not be hired by Amazon. You'll not be hired by Google or Intel if you're not good. Trust me. Have you heard the amount of exams that they have to take? The people prepare to get into Google and then they still get laid off. So they're the best among their peers. But still, so you are good, no doubt. You know stuff. You have 4 out of 4. Everybody has 4 out of 4, maybe, right? But you also have to speak up and participate in discussion, question, intelligent question. That's how. I mean, there is a reason why these companies are billion-dollar companies. They are not like a startup that fails eventually, right? So I hope I make sense. Are you sad for any reason? Don't be sad. Life is like this, essentially. When we were kids, it was all good. Mama and Papa used to take care of everything, but not anymore. We have to take care of ourselves at this stage of life. So this is how life is. But it's not as bad, honestly, right? At some point, you enjoy, become part of the process. It's not really I mean, as overwhelming as you think, but you are basically living the best part of your life, college, right? All right. The other reason, I mean, you may have noticed that I try to give extension almost like, okay, if you have a problem, oh, sure, no problem. Uh, the reason is not like I'm not a politician. I'm not trying to be popular or anything. I'm not getting any votes from you, right? The reason, my philosophy is, I felt as a student, fear, or like if you're worried about something, you're afraid of something like losing grades, making blah, 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 that hinders your learning process. I think like I'm more geared towards getting the grade and getting the points than really learning and challenging myself. You see my point? Okay, so what I'm trying to give you is a platform to overcome fear. Like there is nothing to fear. I will work with you. If something goes wrong, I will be happy to keep making exceptions. Okay, extension, whatever. Like you need makeup exams, I'll give you. It's not a problem. But you have to do your part as well. Learn and be really inquisitive. Take this as a basically as a training ground where you're allowed to fail multiple times, right? You're not being judged here, right? If your friend said, hey, this guy doesn't know this, what's the big deal? It's okay, it's just your friends. They're not your competitors per se as of now, but in industry they will compete with you for the same job, right? So my point is, use the flexibility not just in this, but like in general. College is more flexible. Like here it is more flexible than any other workplace that you can get to. All right. Okay. So sorry, I took a tangent, but I think it is important to get the message across. If you do you have any questions since we took the tangent anyways? Do you have any questions for me? Because you guys seem very sad. Don't be sad. It's okay. It's okay. And if you want to get a way around, by the way, in case you're and if you're like me, because I worked in the industry, it was okay. For example, I mean, again, I'm the person who got the A eventually. So I was selected as one of the, they call it the icon award, like Samsung, something like that. But the colleague that I'm telling you, he was very good friend of mine. We are still friends, very good friends. We still here, like they're also in North America. And By the way, he's working for Amazon right now in a very big post. We're very close friends. So I felt so bad because we work together, we work day and night, blah, blah, blah. So that's how unfair life is. But I realized that I cannot live like this. I need some freedom and flexibility in life. So I decided to pursue grad school and eventually become a researcher, because here, you have flexibility, you can think of stuff, do stuff. So you might want to pursue a research-based career in national labs or in universities. But remember, those positions are limited. They don't hire like Amazon or Google or Intel does. Like they have like 100,000 engineers working in one site, unlike a university where like there are 40 professors. Right? It's very difficult and challenging to go to, but it's not impossible. And there are many universities in the US, of course, many, not one or two. There are thousands of universities. So in case for some of you, if you get stressed out thinking of this, better to think of research-based career, because this is not really cutthroat. But industry, they have to survive. If Intel doesn't make a better chip than AMD, their stock prices will go down and they might get bankrupt. Yes. That's a great question. Yes. So again, remember I just told you about the openness and freedom. Uh, you cannot be creative. Like you cannot ask to artist to draw like a picture like Leonardo da Vinci. Otherwise, I'll fire you. That's not how things work. Or draw something in 5 minutes. Otherwise, I'll fire you. You cannot come up with a masterpiece in a high pressure environment. So you cannot think of. So if I'm always pressured, that come up with a new flip flop. Like okay, how can I like that's not how things work, right? Like open-minded thinking, honestly. So in universities or research labs or research positions, even in industry R&Ds to some degree, they give you this flexibility to think and fail. See, failure is actually a good thing, honestly, in science. If you don't fail, you don't learn anything. If you're doing everything right, that means you're not trying anything new, honestly. Okay. So uh, that's why in national labs and other places, they often give you some degree of flexibility to they're gonna still judge you. We as a professors, we become evaluated every year, but it is not as cutthroat that hey, if you don't do better than the other professor, you're fired. No, right? You're being judged as to whether you're active, whether you're really doing something, or whether you're putting in the effort or something like that, right? But of course, nowhere close to the industry level scrutiny. Nowhere close to that. So they want to give you the openness. There is something called academic freedom. The reason why they give you this is because they encourage you to think. And that, by the way, you might wonder, do they do anything useful? So whatever the industry, right? Semiconductor foundry, whatever. So now we are all using every laptop that you have in the room. It is using FinFET. It is a type of transistor that was invented by a professor at Berkeley. He's still there, Chen Ming Hu, right? He's a very famous professor. So all the big discoveries, all the things that the industry is based on, they were discovered by university people at some point. You see, when I talk about Boolean algebra, somebody, a mathematician, thought about it. But how many mathematicians do you think uh, are working for Amazon now? Not many. Most of these are computer scientists, coding stuff, right? But there are like one or two mathematics folks who are thinking throughout their life and thought about something. Hey, and that changed that game for hundreds of years. So fundamental science research changes the game for the long run. But you don't have like short-term gain right away. Like next year, you cannot sell what we invent. It might take 5 to 10 years or even more to get to impact. But they know this, by the way. If they didn't know, who funds our work? Not just mine, like in general, universities and national labs. There are funding sources. Many of them come from the industry because they want us to take risk. We are risk takers. We have the license to make mistakes, right? Try something, make mistakes, learn from it, and tell them what not to try. Like, hey, don't try this because it doesn't work. Here is why it doesn't work. They also want us to find out why something doesn't work, right? And if it works, that's the best case scenario. Then they can take it and commercialize something. And I just give you one example, FinFET, because it is so ubiquitous. There is not a single electronic device in the room which doesn't have FinFET. You know when it was invented? 2010. And when he was, I might be wrong. Please don't quote me on this number. It could be 12, it could be 8. I don't remember the exact year, but somewhere very close by, not like 50 years ago. Very close. He's still living. And in fact, he's still teaching at Berkeley, for example, right? So you see my point. It's being actively invented and discovered and being deployed in actual practical engineering solutions, right? There are so many other things. So now people are dealing with say hypersonics, and everybody is doing research on hypersonic stuff. How do you handle thermal problem? How do you handle speed? How do you handle blah blah blah? What type of new materials you can develop? So everybody is working together: chemists, material scientists, modelers, mechanical engineers, computer scientists, image recognition people. Everybody is working together from their own side to get something done. Okay, sorry. Anyways, I took a very big tangent, and it's okay. We'll finish this in the next class. I hope at least will something good will come out of the discussion. Anyways, sorry. I'll see you in the next class. All right. Thank you.